We're going to be looking at something this week that I'm actually quite surprised I haven't already covered, because I was thinking about doing some videos on some of the more advanced features of parallel programming and PLINQ, and I realised I haven't even done a basic video just to tell you what it's all about. So that's what we're going to do this week, just look at the very basics of how to do parallel programming, and then I'll do maybe one or two more videos to look at some of the more subtle features we have to it. So let's dive in there and let's take a look at this application that I've written. So it's just trying to do some heavyweight calculations. So what I've done is I've got an array of 100 million doubles, so they will all just be initialized to 0. But then I loop through up to the length of that array, that 100 million, and then of each of those values I calculate the factorial. So I've got a simple little function here called factorial that uses aggregate to multiply each number together. So if we did factorial of 5, it would be 1 times 2 times 3 times 4 times 5. That's how I'd work it out. A couple of other things I've done in there. One is I've modded that value of I with 20 because factorials get very big very quickly. We don't want this to explode. So we've just gone to put a cap on the value. That doesn't matter very much. But then also I've done a +1 because we can't calculate the factorial of 0. Well, that's not entirely true. Factorial of 0 mathematically is valid, it's 1, but the algorithm I'm using here is a bit simple and won't cope with that. So that's why I've just added 1, so we're never trying to calculate factorial of 0. So we loop through that, and then at the end of it all, we just print out the average of all those 100 million calculations. So nothing very clever, but it's mathematically heavyweight. It's going to be using a lot of processing power. And if we run that up, we see obviously we get the console popped up, but we also get on the diagnostics tools, we can see the CPU usage we're making of that. So there's that average that we calculated. That's not really the important thing. But once again, if we just take a look at that, we can see that it's scrolling along at this very low percentage, 6% of all processors. And the reason that's happening is because this particular machine has 16 logical CPUs, 8 physical ones, 16 logical ones. And so when we do a heavyweight processing job and we're not doing any parallelization, then it just has to hog one of those CPUs. So if we look at that in another way, when I run it again, and then we can see we're getting, well, it's using the other ones a little bit. That's probably to do with things like garbage collection, but it's certainly not making maximum use of all the CPUs. And so that's really the point of parallelization. It's not quite the same as multi-threading, because multi-threading can occur even if you've only got one processor, like we used to have 10 or 15 years ago, when it just uses what's known as preemptive multi-threading to switch between which thread is allowed access to the processor. But it doesn't give you any more power. Whereas here, what we're trying to do is, because we've got this 16-core processor, if we're doing a heavyweight job, we want to have the work done on all of the processors. So it does involve multi-threading, but it also has these threads running on different cores rather than just switching in on the same core, which is how it works on older processors. So let's see what we can do to basically parallelize that. And the obvious and wrong way to do it would be to actually generate our own tasks. So we could have a task.run, which runs up another thread. We could divide that work into 16 portions and run them each separately, and the operating system should pretty much put those on the separate cores. But that is really not a good idea. It's far too much work for us to have to worry about, and also it requires knowledge that we don't really have, because as a developer, I know I'm on a 16-core machine, but when this is deployed, it could be on a completely different machine with fewer or more cores, and so we wouldn't be able to make that assumption, so we'd have to do even more work to start interrogating our own machine to find out what's going on there. So it's much better to just use an approach that says to the .NET system, run this in parallel as best you see fit, and let it get on with it. And there's a number of ways we can do that. So let's start one of those. So we'll get rid of the for loop. And then what I'm going to do is use the parallel class, and this has a Parallel.For. So this is a for loop, but it's parallelized, not going to be running on a single core. So you can see what it's put in there for us with its really clever guesswork. We're going to go from 0 to results.length, which is 100 million. I'm actually going to change that because this will start going too fast for us to really see what's going on. So let's make that 500 million. And so it's going to loop through like a for loop in that range. And then we have a lambda expression to give us the actual body of what's going on. So it's given us I as the loop counter effectively, which is the parameter that's passed in there. So if I take exactly this same code and put that in there, then it's still going to do the same thing. It's going to loop through and put those in there. But if we run that one up, and again, look at there, you can see the processor is doing much, much more. So it's getting on for 100%. And we saw also that even though we got 5 times as many to calculate, that was going rather quicker. And if we bring up the task manager once again and go back to the CPUs and do that again, then we can see we're getting a big peak on all of those logical processors. So it's parallelized that for us very well. Now, the exact details of how it's done we'll talk about in a later video, but basically in a pretty simple case like that, what it's just done is taken that 500 million, roughly chopped it into 16 parts and done each one of those and then recombined it. Another thing you'll notice there though is if we look at the CPU here, there it's using lots of it, but then at the very end you can see we get that little flat bit where it's back to 6%. I'll just show you the image of that so you can see what's happening. And what's happening there is although we have parallelized all of that, that average is still being calculated on a single processor. And we'll see a bit later on how we can sort that out. Let's just do something else in there just so we can actually really see what's going on. So what I'm going to do is introduce in here another collection, and I'm going to do a thing called usage. And this I'm going to have as a new, and then I'm going to use a thing called a concurrent dictionary. So it comes from a separate namespace. And as the name suggests, the concurrent dictionary is just like the normal dictionary that we get in system.collections.generic, except it is thread safe. So with a normal dictionary, if we started adding things to it from different threads, we'd get into trouble if you got any kind of clash. But a concurrent dictionary has its own safety checks in there. So we don't have to write our own locks and things on a normal dictionary, we can just use a concurrent dictionary. And this is going to be a concurrent dictionary that is keyed on an int and takes an int, and what this is going to do is store the number of times that this loop has gone through on each thread. So if we put in here, I'm going to say usage, and then we've got a method called add or update, and what we're going to do with that is get hold of the thread ID, so we can get hold of that from environment.current managed thread ID. So that's going to be the key. And then we're going to give it the default value if we're adding it for the first time. And then we have a lambda that says what we're going to do on subsequent times. And so we're just going to return count plus 1. So I've got a discard there. You get some other information in there that I'm not interested in with that discard. But basically, that's the way that we can count those up. And then after we've printed out the results, I'm going to say console write line, and then I'm going to say usage.count threads used. And then I'm going to have just a regular for each that's going to go through each of the items in the dictionary. And then we can do a console write line, and then we'll say thread and then pair.key, because remember that's the thread ID that we've just been putting in up there, and then we'll say used and then pair.value, which is the count that we've been counting up times. Okay, so that's actually going to slow things down quite a bit, having to add something to this concurrent dictionary on every iteration, but it'll show us what's happening. So if we run that one up, we can still see it's doing the same sort of thing. As I say, probably doing a bit more because of adding to the dictionary. But then you can see it's given us the average. It said it's used 18 threads, and then it's given us the ID and the usage on each one. And we can see they're roughly the same kind of values we have there. You might think it's a bit odd that we've used 18 threads, even though I've only got 16 logical cores. But remember, it's not an exact one-to-one mapping between them. We'd find if we dug really deep down that some of those threads were actually using the same core. It's just the way it allocates threads is not exactly the same as the way it allocates cores. But there we can see that whole thing is working, doing the sort of thing we want. So that's one way to do parallelization, using the Parallel.For. Another thing we can do is use Parallel.ForEach. Now, probably not quite as good in this situation, but I'll show you how we can do that. So what we'll do is another comment out of that. And then what I'm going to do is we will have a var values, and then we're going to say that equals, and then we can say enumerable dot range. So just gives us the range, a bit like we had in the factorial, in fact. And then we're going to have that as a range from 0, and then it's going to have results dot length elements in there. So what that does is it will give us an enumerable of 500,000 elements that automatically are going to have values 0, 1, 2, 3, all the way up to 4999999. So that's what we've got there. And then having done that, we can do the for each on this. So now instead of the Parallel.For, we do a Parallel.ForEach. And actually the auto-completion here has done something a bit confusing, because it's called that second parameter on the lambda, it's called it index, but it's not index. It's this thing called parallel loop state. It's not going to give us an index because you don't get an index in a for each. And in fact, that one, because I'm not going to use it, I'm also going to turn into a discard. So that's what we're going to have there. And the problem is, because we don't have an index, we can't just do something like results I. So I'm actually going to have another collection on there. So what I'm going to do here is have a var, and I'm going to call this results bag, and this is going to be of a type concurrent bag of doubles. So like I had a concurrent dictionary, another thread safe collection concurrent bag that we've got there. And so what we can do here is just say results bag dot add, and then we don't want to add the value, we actually want to add again the factorial in there, and change that to value. And then let's also just keep track in the same way. So let's pop in that usage count. And then lastly, we just need to change that results.average to resultsBag.average. And then if we run that up, and again, we can see it's doing the parallel processing. It's using most of the processing power. There will obviously be differences in terms of performance with doing this same job with the for and the for each. Not really going to discuss them here, but it's the sort of thing you might want to do testing. My guess would be here that the for loop is probably a bit faster because we don't have to generate that initial collection. But it's up to you to test on that. But again, we can see it's used 18 threads. We can see the numbers. We can see how it's used all that. So that was our Parallel.For and our Parallel.ForEach. Similar tools, but for slightly different situations maybe, but you can see they do the job very nicely for us. We don't have to do very much worrying about the multi-threading. We've got to be a bit careful by using things like the ConcurrentBag and the ConcurrentDictionary, but we've not had to worry about working out how to split up this big job into smaller parts. We don't have to actually know how many cores are available when we're programming. That said, the one that I would tend to use most of all, not absolutely always, but certainly the easiest one to go with, is actually to use the idea of PLINQ, which is parallel link. And the way we can do that, well, let's do this job just with regular link to start with. So what I'm going to do is comment that out, and then let's do the same thing, but just using link. So I'm going to say var, and then we'll call these link results, equals, and then we can say from val in values, and then simply select, and then once again we'll have the factorial calculation, change that to val, and then also we can put the average straight into that. So I can then wrap all of that up in brackets and just do the dot average on that, because there's no keyword average in LINQ, but we can still use the extension method. And then here I can just take that and pop that one in there. Not going to get any usage and thread counts as yet. We'll come on to that in a moment. But bear in mind, it's not going to be very interesting because this is not yet PLINQ. This is just regular link. And in fact, because this is going to be much slower, I'm going to reduce that back to 100,000. And if we look at that, then we can see we're back to where we started. So it's just down there at that roughly 6%, that 1/16th, and gave us the result out there, but no count of threads used. Let's just turn that into PLINQ, and that's really easy to do. So I'm going to pop that back up to 500,000 because it's going to be a bit too quick. And then all you have to do to get PLINQ is on your data source, which is our values, we say dot AsParallel. Okay, so as simple as that. That is how we tell it to do the parallelization. So Parallel.ForEach, Parallel.For, fair bit of recoding compared with the standard for loop, but going from LINQ to PLINQ is as easy as that. Bearing in mind, this only makes sense when we're dealing with LINQ to objects, so where we're dealing with data in memory. If this was LINQ to entity framework or something like that, you can't parallelize that because the work isn't running in your process, it's running on your database, which will do its own parallelization tricks, but it's not for us to worry about. So this is only LINQ to objects. But having done that, if we run that one up, we can now see we're back to where we were before. So it's managed to do that all in one go. Still, we're getting that result, but we are still on 0 threads used. How can we just keep track of the threads? Well, we've got to do a little bit of a trick here because we've got to effectively introduce what we call a side effect into that LINQ query, because the LINQ query is just taking our incoming data, the values, to our outgoing data and averaging them. So what we could do actually is down here, I'm going to put a method that's going to return a double and is going to be called count, and then is going to take a double, which we'll again call val. And what we could do actually is, in its simplest form, we could just say that it returns val, and then if we take that thing in the select and wrap it up in count, then that will actually have no effect at all because we're just taking the value and returning it, so it'll still be what is selected and then average. But now we're inside count, we've got the really nice thing that we can take our usage tracker that we've been using before and we can pop it in there. So you can see we've got that in there. So as well as just, in a sense, doing nothing because it doesn't modify the value, it just returns it, we've now got this side effect along the way. Not something I'd particularly recommend in regular programming because side effects can be confusing if you don't realize what's going on and it's not obvious. But in this case, because we're just trying to demonstrate the feature, I think it's perfectly fair. So now if we do that and run that one up, you can still see obviously that it's doing it in multiple processes. But now we've got it that it's giving us that count, and we can see it's doing basically the same sort of thing in terms of distribution. So those were the 3 ways we had to do it. Well, 4 ways really, if you include the really bad way of just doing it without parallelization. But we had the Parallel.For, we had the Parallel.ForEach, and the one that I think is generally easiest to program because it's just adding that one function call, we've got the PLINQ, the parallel link. One other thing though, just to point out on that, you might have noticed when we did it with PLINQ that we didn't get that little tail. Remember I was pointing out that the average was being done without parallelization when we did it in some of the earlier examples. But if I run this one up and we take a look at the CPU, you can see it's staying high, staying high, staying high, and it's high all the way, and then it's finished, and we didn't see that little tail. Whereas if I just go back to Parallel.For, let's say, then we can put that back in. And the reason it wasn't there is simply once we've gone AsParallel, then with PLINQ, we are AsParallel all the way through, unless we actually choose to turn it off, which we'll look at in a later video. But that means that average is actually automatically going to be parallelized. So if we do that, let's change that one back to look at results.average. So if we run that, then we can see now it's starting out in the Parallel.For using all the processing power, but then at the end it drops off to that very small bit of using just the one core for the average. But all we need to do is in here we can also put the AsParallel. So that one will now force the average, because remember the average is a LINQ extension method, to use it just as it did over here, because we've done the AsParallel earlier on. So we can use it like that as well. And if we run that, we'll then see that it's not going to have that tail on the end if we let that go to the end, so that went straight away. But really that's starting to be quite clever. It's easy enough to understand how the Parallel.For works because all of these calculations are entirely independent. We can just break it down into those 16 chunks and separately do the calculations on each one. But an average is rather more complicated than that because the average obviously has to combine data from various bits and pieces. So it's doing some quite clever stuff there, but that's going to be the subject of one of the later videos, how it can actually combine results and that sort of thing. For now, we're just looking at the basic idea, the three approaches, Parallel.For, Parallel.ForEach and PLINQ. So hope that was useful. If you enjoyed it, do click like, do subscribe, and I'll see you next time for some more on parallelization.